Hello everyone, we are from Group 2. For the flipped classroom, we are going to explain about the topic of characterization of polymer using infrared spectroscopy. Our group consists of Irene, Fong, Neely, and Amina. So we hope that you do enjoy our presentation for this topic.
Hi everyone, I'm Amina. I will present the introduction of infrared spectroscopy. Infrared spectroscopy deals with the infrared region of the electromagnetic spectrum. As we can see in the electromagnetic spectrum, the infrared region just next to red in the visible region. It has a longer wavelength and lower frequency compared to visible light. Generally, spectroscopy depends on the interaction of atoms or molecules with electromagnetic radiation. So, infrared spectroscopy detects frequency of infrared light that are absorbed by a molecule, which causes vibrational transition in the molecule. The major use of IR spectroscopy is to measure the bond vibration frequency and is used to determine the functional group. For infrared spectrum, the absorption of IR radiation is recorded in the absorption or transmittance peak versus energy level. Wave number is most commonly used in IR, also expressed in unit cm to the power of -1 or reciprocal of wavelength in centimeter. Sometimes wave number also referred as frequency.
How does the method work? The infrared radiation is split into two beams from the same source passing through the sample and reference chambers. These reference and sample beams are focused on the detector by making use of an optical chopper such as a sector mirror. One beam passes through the sample cell and the other passes through the reference cell. The reference cell is used to measure the effect of the material of the sample cell, the solvent, and the conditions of the atmosphere so that these effects can be discounted from information retrieved by the sample cell. After the incident radiation travels through the sample species, the emitted wavefront of radiation is dispersed by a monochromator into its component frequencies. A combination of gratings with variable slit mechanisms, mirrors, and filters comprise the dispersive system. The difference in transmittance between the sample and the reference cell is because of the absorption of certain frequencies by the molecules of the sample. Narrower slits give better resolution by distinguishing more closely spaced frequencies of radiation, and wider slits allow more light to reach the detector and provide better system sensitivity. This absorption then results in change in the vibrational energy of the molecule under examination. This is picked up by the detector by hitting the detector and generates an electrical signal as a response.
After listening to the explanation on what is infrared spectroscopy and how does it work, let us move on with some example on what are the important information that we can extract from IR spectrum and how it can do with the characterization of polymer. In this video, I'm going to give 3 examples related to the characterization of polymer. The first one will be the chemical structures of unknown polymer can be recognized by analyzing the IR spectrum with the reference of IR table, which contains the information of infrared stretching frequencies of typical bonds. This figure shows the difference of IR spectra between polyimide and its chemical repeating unit model compound. We can recognize that there is a significant peak at a frequency of 650 to 900 cm-1, which indicates the p-substituting linkage between the aromatic structure of monomers with CH binding. Secondly, the structural configuration of polymer can be differentiated by using IR spectroscopy. So, I'm going to use polystyrene as an example. Polystyrene can have either an isostatic or astatic structure. Isostatic polystyrene, which means that all the aromatic rings are on one side of the carbon backbone, while for astatic polystyrene, the aromatic rings are on random sides of the carbon backbone. This difference in configuration affects one of the major physical properties of polystyrene. For astatic polystyrene, which is the commercially available polymer, is highly soluble in chloroform, while for isostatic polystyrene, it is insoluble in chloroform. This figure shows the spectra of isostatic and astatic polystyrene. It can be seen that although the gross spectral features are similar, there are a number of small, subtle, but significant differences between the two spectra. In the 1365 to 1197 cm-1 region, a number of differences are evident in the profiles of the bands. One of the most significant differences is observed in the region of 1060 cm-1. The isostatic polymer has a doublet which has a value of 1080 and 1055 cm-1, while for the astatic polymer, it has a singlet at 1065 cm-1. Besides that, the astatic material has a band at 940 cm-1. In the longer wavelength region, the isostatic polymer has a band at 558 cm-1 with a weak but definite shoulder at 585 cm-1, whereas the astatic polystyrene has a band at 538 cm-1. Lastly, polymorphism can be monitored by using IR spectroscopy as well. All of the changes can be recorded and displayed onto the IR spectrum. So, what is polymorphism? Polymorphism is the ability of an object to take on many forms. For this statement, I'll be using isostatic polybutene 1 to explain about it. Isostatic polybutene 1 can exist in three different crystalline forms which can be distinguished by infrared. These three forms has been designated as 1, 2, and 3 by NATA. Two of these forms, 1 and 3, are considerably stable relative to form 2, which is unstable. Modifications 2 and 1 are produced by hot molding a film of the material and allowing it to age at room temperature for a period of time. If the spectrum of the film is recorded directly after molding, modifications 2 is obtained. After aging approximately 30 minutes at room temperature, spectral changes can be observed as unstable modification 2 gradually transform into stable modification 1. For approximately the next 3 weeks, spectral changes associated with 2 to 1 transformation occur that can be followed by infrared. After 3 weeks, the transformation is essentially complete. Modification 3, which is also stable, has been assigned to an orthorhombic structure and is obtained either from single crystal preparation or casting a film from solution. So, for this figure, it shows the changes that occur during the 2 to 1 transformation. For 2A, it shows the spectrum of polybutene 1 30 minutes after molding the film. This is essentially the spectrum of modification 2. The arrows indicates where the major spectral changes occur. For 2B, it is 3 hours later, an extensive 2 to 1 transformation has occurred. For 2C, it is 3 weeks later, and a 2 to 1 transformation is virtually complete, and it is also the spectrum of stable modification 1. The 2 to 1 transformation involves the 4-fold helix of modifications 2 expanding to a 3-fold helix. and the resulting changes in the intermolecular interaction being reflected as the spectra changes. So, to summarize, this figure shows the spectra of all three modifications. The differences in the spectra are readily apparent and can be used to identify all three modifications. So, that's all from us. Thank you for your watching, and we really hope that you get some insightful information from our presentation.